Welcome back, everyone. In this video, I will introduce the last intermolecular force that we will be learning about, and then I will summarize all the intermolecular forces I've covered in my lecture videos. In addition, we will practice a couple of problems together. All right, so the last intermolecular force and the strongest one is the ion dipole force, and this is when an ionic compound is mixed with a polar compound. And like I said, it's the strongest intermolecular force. And we will investigate it further in future lecture videos when I go into the topic of solutions and understanding why solutions mix. So we'll definitely have a lot more time with this particular intermolecular force in the future. But just to give you an example, let's say we have sodium chloride. Sodium in water breaks up into a cation, and the water molecules surround it such that the oxygens are facing towards the sodium. And why do you think that is? Good. Hopefully it's because you said that opposites are attracted to one another. Oxygen's more electronegative than hydrogen. And there's a lot more water molecules. I'm only showing a few here. And so the overarching theme in chemistry, opposites attract. And so these water molecules are really attracted to that sodium cation, specifically the oxygen atom of the water molecule is. And so it will form a little shell around it, a hydration shell. And same thing goes for the chloride. It's negative, and so which atoms in the water molecule would be attracted to that? Excellent. It would be the hydrogens because they're partial positive. And once again, you're always telling yourself opposites are attracted to each other. And so it would face like this. And remember, these are just interactions, so we only use dotted lines to represent them. Fantastic. So let's just go through a quick overview here. So the weakest intermolecular force is dispersion, and on this side of the chart, we have the strength, and so this is in kilojoules per mole. And this is present in all molecules and atoms, but if you were to ask, which one is it the dominant intermolecular force? Well, it's the dominant intermolecular force in nonpolar molecules or monatomic gases. And this gives you a molecular perspective of what's going on here. So remember, it's a transient dipole, and so that's why we're looking at the electron cloud here to see that, at one point in time, the electron cloud reacts to another nearby electron cloud, creating a transient dipole, but it's not a permanent dipole. Then we studied the dipole-dipole intermolecular force, and this is dominant in polar molecules that don't have hydrogen bonding. And as you can see here, these molecules, because they're polar, they have a permanent dipole moment. And so when they interact with another molecule, then they have a stronger intermolecular force, and that's the dipole-dipole force. And this is the energy or the strength associated with this interaction. And then we talked about hydrogen bonding, which is like a subcategory of dipole-dipole. It's a super dipole-dipole force. Remember, this happens when molecules contain hydrogen bonded to fluorine, oxygen, or nitrogen. And that's because their particular permanent dipole moments within the molecule are very, very strong, good charge separation, and so therefore the interactions between the hydrogen and that very electronegative atom are really strong and distinguished as hydrogen bonding. and you can see the energy associated with that. And then finally, we just covered briefly ion-dipole intermolecular force, and that's when you mix ionic compounds with polar compounds. Because we're in a general chemistry course, generally the polar compound we're referring to is water. We're working with aqueous solutions, right? And so you can see here, this is a cation, and those oxygen atoms, which are usually represented in red when you look at these space-filling models, are surrounding it, forming this hydration shell. And we can see that's a very good strength for this intermolecular force. Now, intermolecular forces is a topic I'm spending a lot of time on. You know, your first semester general chemistry professor may have covered this topic already. And so hopefully, if that's the case, and that's great. That's review for you, right? However, I'm really passionate about reviewing over it again because this topic is important for a lot of different reasons. I gave you one reason. For example, when we studied hydrogen bonding, I showed you a video on DNA and its structure and how hydrogen bonding plays a critical role in that. And so it's something that it's really important for students to master because it's not only going to be used in my class, but in future STEM courses as well. So it's important you build that strong foundation now with me. However, I realized, in my years of teaching that this topic it's tough. It was tough for me when I was a student to really understand. It doesn't feel very tangible. And so I had a student in my class a few years back, and we were discussing this. She had become a tutor eventually for another class, and she was like, yeah, students are really struggling with intermolecular forces. And I was like, yeah. And she's like, I'm going to come with some creative ways, some cool analogies to help students understand it better. And the student now is getting her master's in education. She's going to graduate soon, and she'll be a chemistry high school teacher. And I'm just so proud of her. And she has told me and given me permission to use these handouts that she's created. And since then, I've taught several courses of second semester general chemistry, and students really appreciate it. So I wanted to share this information with you. It's very creative, and you may think it's silly, but sometimes the silliest analogies or metaphors really can help us master a difficult concept. So let's get started. Like I said, these were created by one of my former students, Hannah Hahn. And so we're going to start with the dispersion forces. And the way she lays out this context here is, imagine you're a human, and the human's composed of a physical body and a soul, or ghost, right? And she's kind of assigning this partial positive and partial negative. Much the same way a molecule has regions of electron density and lack of electron density. Okay. And so, much like all humans have a body and a soul, all compounds have dispersion forces, temporary partial positive and partial negative regions. Now, how does this work? Well, imagine that you have a human and he loses his ghost or soul. I'm going to call it a ghost because it looks like one. It's kind of cute, right? And it gets near into another human. And when that happens, that scares this human's ghost away, and so on and so forth. So there's like these interactions based on nearby neighbors, right? So as the ghost of human 1 approaches human 2, this scares that human 2, causing its ghost to leave, but the body of human 2 remains. So analogous to that, a chemistry example was the helium atom we looked at here. And you can see here that, maybe this helium atom and electrons are located really close on this side, leaving this side partial positive. But then those electrons scare the next helium's electrons far away, and so this is left partial positive. And now it can create that transient dipole moment, which is the attractive intermolecular force, and so on and so forth. So it's kind of cool to see these, this analogy here, I'm hoping makes a little bit more sense about how the electrons are behaving in the electron cloud. So what determines the strength of dispersion forces? Well, it's based on size and also surface area. So let's look at size. How well can a molecule polarize? And remember, what does polarize mean again? It means for electrons to move. Good. So its ability of electrons to move in response to a neighboring temporary dipole, which results in the separation of charge, that dipole moment, in the molecule. And so I love this analogy here. Think of bubbles, right? Think of comparing a small bubble to a very large bubble, right? My daughter loves these huge bubbles that you can make with those ropes. They're so cool. All right, so a small bubble, if you think about this here, and also at the same time you can be thinking about small molecule versus large molecule and these hydrocarbons. A small bubble is not as easily distorted by the wind. And so the shape of the bubble doesn't change much due to the wind. However, if you had a large bubble and it was getting windy, it can be easily distorted by the wind, and the shape of the bubble responds quickly to the wind, right? Remember from quantum mechanics, size of the molecule is determined by that electron cloud, right? And so the larger the molecule, the larger that electron cloud, or the larger that bubble, right? Now, if you have something that has a small electron cloud, then those electrons are really close to the nucleus. And what charge is the nucleus? It's a positive charge, and that means this is it's not as polarizable because those electrons are being held as tightly. They're not as easily influenced by neighbors. Whereas if you look at something like this that has a larger electron cloud, they're farther away from the nucleus and therefore not held on as tightly to that positive core. That means these electrons that are in this big bubble here are more polarizable, and that means the electron density can move in response to neighboring charges. So the conclusion we can have here when we're talking about size in reference to dispersion forces is that the larger the size, for example, the molecular weight, the more polarizable that molecule or atom can be, and therefore it will experience stronger dispersion forces when it interacts with other molecules or other atoms. Now, what about surface area? That's the other key factor. Now, let's say we have molecules that have similar molecular weight, and they're constitutional isomers, right? They have the same molecular weight but different structure. You can think of something that's long and linear versus something that's spherical or branched, right? So the analogy here we're using is ice cream. So you can think of having an ice cream bar, which is pretty flat, or something that's like a cone, right? Where you have spherical ice cream. And so, which one is easier to stack? Well, yeah, it would be the bars, right? And that's because they have more surface area. Same thing here in this example, an example I had shown you in a previous video, that this pentane molecule can stack more easily, even though these are constitutional isomers. And that's because it has more surface area and therefore allows for stronger dispersion forces to happen. So when you're thinking of dispersion forces and you're looking at the relative strength, if you're comparing different molecules that are all experiencing dispersion forces, you get to think of size and surface area. And I'm hoping that these cute little analogies here will help you visualize what is happening in the molecules that are experiencing dispersion forces, as well as, if you're working with a monoatomic gas like the noble gases. Now, I really love this handout that she had created. This is looking at all the intermolecular forces, and so kind of overviewing those four, and then also kind of giving you some really cool analogies to think about here. So let's start with dispersion force. It's the weakest. It's present in all compounds, mainly in nonpolar. It's the dominant force in nonpolar molecules or noble gases. We just reviewed over how the strength is determined by size and surface area. And remember, it's just a temporary transient dipole moment. Now she equates that to let's say that you just met a friend, right? You just met a person, you have like an acquaintance relationship. And so you might meet this person, you want to interact with them, and you say something like, oh, nice hair, right? But then you just go on about your day, right? Then the next strongest intermolecular force is the dipole-dipole, and this happens between polar molecules, and we're not including hydrogen bonding in this one here. These molecules do contain permanent dipole moments. So in this case here, this is formaldehyde. And so there's a permanent dipole moment. And so when it interacts, it's a stronger interaction than dispersion. And you could think of this relationship as something like dating, right? Where you're dating someone, you're getting closer to them, you're attracted to them, you see them more often than you would see just an acquaintance. All right, now we have hydrogen bonding, and this is still between polar molecules, but the hydrogens bond it to nitrogen, oxygen, or fluorine, right? And this is generally stronger than dipole-dipole. That's why it's in its own little kind of category here. You can think of this as a marriage, right? And so, it's a little bit of a stronger commitment than if you were just dating someone in the early parts of dating, right? All right, so then the last one is the ion dipole, and this is between an ionic compound and a polar compound. Like I said, usually the polar compound is water, because that's the solvent we use in general chemistry. And so we have that sodium chloride example I just went over, and I love how she equates this to the relationship between a parent and a child, right? I'm always kind of keeping a really close eye over my children to make sure they don't get hurt. They're really little right now, and so, I'm always kind of keeping an eye on them, and so that's a very, very strong interaction. And I love that kind of analogy there. So once again, when I share these with students, initially at first, they may think, oh, it's kind of silly, but I promise you, if you start to develop tools like this, where when you're learning something that's really complicated and you try to relate it to something that you can understand in the real world, then that will help you learn that material that much better, right? If you can make some sort of connection to a concept or an idea that is familiar to you. Okay, so I hope this helps. And you can share it with other people if you have a friend who's also learning about intermolecular forces, and try to teach them using these types of analogies, and hopefully you can have fun with it and get creative with it. All right, so let's just practice a couple of examples together. How would you approach these types of problems? Right? And so we will use the knowledge from first semester general chemistry. It's really important you feel comfortable writing Lewis dot structures, deriving molecular geometry, determining if a molecule is polar or non-polar. So we're kind of bringing a lot of that in here. And that's why I recorded some videos to help you all review over first semester general chemistry and some of the important topics there. All right, so let's go ahead and get started. The first one is carbon tetrabromide. And carbon tetrabromide has how many total valence electrons? And you can pause the video and try to do this on your own first. I always highly encourage that you do when I practice problems with you. And so then you can check your work and see, do I actually understand this material? Or do I need a little bit more help? All right. So it has 32 total valence electrons to work with. The least electronegative atom is bromine. Not bromine, my apologies. It's carbon. I wrote carbon and I said bromine. All right, so let's just go ahead and connect everything together before I get ahead of myself. So 4 bromines. Then you fill the outside atoms octet first. So I'm going to fill in all these lone pairs. And how many electrons have I drawn in total? Right, I've drawn in 32, and so this is 8. 8 times 4 is 32. No leftovers, so no lone pairs on the central atom. And the central atom already has an octet, so we're good to go here. Now, how many electron groups do I have attached to my central atom? Excellent, I have 4 electron groups, which means what is my electron pair geometry? Good. It is tetrahedral. And my molecular geometry is also what? Tetrahedral. Very good. What's the bond angle? 109 degrees. Good. Now, it's important that we draw it in 3D. And I mean, obviously, the question actually asked that as well, right? We went 3-dimensional, which means we have to use bold and wedged lines if it's needed. In this case, it is. And so for tetrahedral, 2 of them are in the plane of the paper. 1 is bold, coming at you, and then 1 is dashed, going into the paper. So this is what tetrahedral geometry looks like. And the carbon-bromine bond is kind of borderline polar covalent, non-polar covalent. The Linus Pauling electronegativity values is not like a clear cut, if you're at 0.5, this is what it has to be, like it's polar or not polar. There's more to it than that. However, it is kind of a good guide. If you learn the electronegativity values, it's a great guide. But once again, just understand it's not, the only thing that we use. A lot of what we use is based on looking at chemical reactions and observing how molecules have behaved and then establishing those structure-property relationships that way. So generally speaking, the carbon-bromine bond is actually considered polar covalent. And so we've got 4 of them, in here. And bromine's more electronegative, so you would draw the little dipole arrows pointing towards the bromines. But even though it has polar covalent bonds, is this molecule polar or non-polar overall? Good, it's non-polar. That's because this molecule is symmetrical. Okay, and so due to the symmetry, the little dipole moments cancel one another out. Okay, fantastic. So, with that being said, if it's non-polar, what is its dominant intermolecular force? Good, it's dispersion. All right. I know I didn't ask it in this question, but let's go ahead and illustrate that dispersion force taking place. So remember, to draw intermolecular forces, we need to show 2 molecules at least to show that interaction. So I'm going to draw another carbon tetrabromide molecule next to the previous one I have drawn. I'm also going to draw it in 3D. I think it's important to start thinking in 3D. It's a skill that you have to learn. It took me a while, but once you do it, you'll definitely feel comfortable, I'm sure. Now, because dispersion forces, like all these dipole moments are canceled out. So overall, like the electron density is pretty evenly distributed here. But remember that we have a big electron cloud, and the electrons are still moving. It's dynamic. And so when this molecule here gets close to that molecule, then the electrons are going to move around such that they don't want to be anywhere near each other, right? So let's say hypothetically I took a picture of this molecule, and at this point in time, the partial negative charges on this molecule and the electrons are really located on the right side. Like I said, this is just all hypothetical. Then if that's the case, then the electrons that are in this molecule are going to run far away. So if you remember that human and ghost analogy, it was like, the ghost is leaving, right? And so if that's the case, then what we're left with here on this side of the molecule is partial positive because the electrons got scared and they moved away. And when that happened, we created these little temporary dipole moments, these transient dipole moments. And this is the dispersion force. Dispersion intermolecular force. Remember, always represent as a dotted line. And if you have to represent it, then it's okay to just show a bunch of partial negative charges on one side of the molecule or atom and partial positive charges on the opposite molecule or atom, and then just show a dot, 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 right? This is just saying like it's not permanent, and it's just the electron cloud is just, more electrons are on this side than they are on the other side, okay? All right, let's do the next example. And we have dichloromethane, also known as methylene chloride. It is also going to have tetrahedral geometry, and you can count the total number of valence electrons. Check the work, right? So that's what it looks like here. 4 electron groups, 109 degrees Celsius. Not degrees Celsius, 109-degree bond angle. And if we look at this here, the carbon-chlorine bond is polar covalent. The chlorine is more electronegative than the carbon atom. Now remember, carbon-hydrogen bonds are nonpolar, and so these hydrogens do not have a partial positive charge. I think a lot of times students just want to give hydrogens a partial positive charge, but that's not the case here. These are nonpolar covalent, so the electron density or the electrons shared in this bond are pretty evenly distributed, so there's no partial positive there, okay? All right, so with that being said, is this molecule polar or nonpolar? This molecule is polar, and that's why it's really important to draw this in tetrahedral, and that's because these little dipole moments don't cancel each other out, right? It looks almost like a bent shape here, and if you were to build the model, it would be like in that it's a 109-degree bond angle, right? So it's polar. What is the dominant intermolecular force then? Dipole, dipole. Excellent. You always have to ask yourself, if it's polar, you have to ask yourself, is hydrogen bonding taking place? But it's not, because that has to be a hydrogen bond at 10 nitrogen, oxygen, or fluorine, and that's not the case here. All right, so how would we illustrate this? Then you would need to draw another molecule of dichloromethane right next to it. And because there's permanent dipoles, then you need to indicate them using partial negative and partial positive charges. That's really important for polar molecules, is to draw those in. The arrows are, also important. However, and especially if you enjoy math and you understand vectors, you can think of these as vectors and that they don't cancel each other out, and like the overall vector is here. And some of you may be interested in that, and that's great. But just simply using the partial negative and partial positive notation is a great way to illustrate your knowledge of where the electron density is really located in the structure itself, okay? So when we see this here, remember opposite charges are attracted to each other. So it doesn't matter which chlorine I choose, I'm just going to choose one chlorine, and it is not interacting with this hydrogen, it's interacting with this partial positive carbon in the other structure, and you just need to show one. So this is the dipole-dipole intermolecular force, always represented once again by a dot, 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 because it's just an interaction. They interact and then they move on and they interact with another molecule, right? And this dipole-dipole intermolecular force is stronger than this dispersion force here. Now, these molecules do experience, this dichloromethane or methylene chloride experiences dispersion forces. They all do. However, the dominant intermolecular force of dipole-dipole is stronger and therefore determines the properties of this molecule. Higher boiling point, higher melting point, etc. Okay? So that's how I would approach these problems. Once again, practice, drawing Lewis structures, determining molecular geometry, because if a molecule has symmetry, then little dipole moments can cancel out like it was in this case here. And knowing if this is polar or non-polar helps you to determine what the intermolecular force will be. So I hope that this strategy helps you out, and just keep practicing those problems. Let me know if you have any questions. Thank you all for watching, and see you next time.